Hello, this is Mr. Huber. In this lesson, we're going to learn about exponential growth and decay functions. Okay, an exponential function is written in the form y equals a times b to the x. So we still have an x and a y like in most equations, and the a and b values are going to be our keys here. A is the y value and x is 0. That means it's the y-intercept, right? The y-intercept is always the value when x is 0. So we'd have 0 comma a as our y-intercept. So again, the a value is always your starting amount when x is 0. B is the growth or decay factor. It's growth if it's greater than 1. If it's between 0 and 1, it's decay. So if we have a B value of 2 or 3.5, it's going to be growth. If it's between 0 and 1, a fraction like 1/2 or 0.8, okay, if it's 3/2, that's greater than 1, that'd be growth. But if the B value is between 0 and 1, it's decay. So let's see what that looks like with some tables of values. So a table of values here, where we have x values and y values, and we want to notice as the x's go up by 1, what's happening to the y values. Unlike a linear equation where we'd add the same amount each time, now we're multiplying by the same amount each time. We're multiplying by 3, then by 3, by 3 to get the next y value. If you're wondering, how do we figure out if that would be multiplying by 3 if that wasn't given to us? Well, you take a y value and divide by the y value before it. So if I do 18 over 6, that's 3. If I do 6 over 2, that's 3. So you can take a y value, divide by the y value before it, and you'll get the b value. So in this case, the b value is 3. Our a value is right here, right? That's the y value when x is 0, 0 comma 2. So we'd have an equation for this. It would be y equals 2 times 3 to the x. All right, in the next example, right, as our x values go up by 1, what's happening to the y values? And if you don't recognize here, and you don't want to look at it as dividing, you always want to look at it as multiplying. So dividing by 4 would be the same as multiplying by 1/4. And we could find that out by doing 1 divided by 4. Well, that'd be 1 over 4. If we have 1/4 over 1, 1/4 over anything over 1 would be itself. So we'd have 1/4. And then we do 1/16 divided by 1/4. You can put it in a calculator, or it's 1/16 times 4 over 1, right? Dividing by a fraction, that'd be 1/4. So our b value would be 1/4. Our a value would be 1. So we'd have y equals 1 times 1/4 to the x. You don't have to write the 1, and you could put the 1/4 as 0.25 as well. That's the same thing. All right, you want your a value, which is the y value when x is 0, and your b value, which is what you're multiplying by to get each next y value. Take a y value, divide by the 1 before it, and you'll have what that b value is. All right, now let's practice writing a rule for these functions. So we want the a value. The a value is 27. Right? It's the y value when x is 0. I'm going to take each y value and divide by the 1 before it. Divide by the 1 before it. We could keep doing that. That's going to come out to 3. That's our b value. Make sure it's the same all the way across. So our equation is going to be y equals 27 times 3 to the x. If we want to check and see if that works, right, we could take any of these x values, plug it into our equation, we should get the y value that goes with it. So if I plug a 1 in here for x, I should get an 81 for y. And so you can always check and make sure that your rule that you're writing in your equation actually works. Okay, in this next problem, again, I'm going to take 1 over 5, 1/5 over 1, which is 1/5. These are all my b values of 1/5. And my a value is 1, so I get y equals 1 times 1/5 to the x. You could write that as 0.2 to the x. 1/5 you could put as a decimal 0.2, that's fine. All right, so you want to find that b value by taking y values, dividing by the 1 before it, and the a value is always the y value when x is 0. All right, let's look at what we could do for graphing. When we graph an equation in 2 variables, any equation in 2 variables, we're graphing all of the ordered pairs that are solutions to that equation, right? Plug in an x, you get a y, that solution is part of the graph. So we can make a table of values, get some x's and y's, and put those on our graph. We're going to be able to do that with exponential functions as well. In this problem, we're going to make a table of values. We're going to say x, y. For x, we're going to plug in -2, -1, 0, 1, and 2. Right? So when I plug in 0, let's just start there. Right? If I plug in 0, right, 5 to the 0, anything to the 0 power is 1, which is why our a value, which is 1, that's why that a value is always our y-intercept, because 5 to the 0 is 1 times whatever the a value is. So in this case, it's just going to be 5 to the 0 is 1. We plug in a 1, 5 to the first is 5. 5 squared is 25. Recall what happens with a negative exponent. If we have 5 to the negative first, it's the same as 1 over 5 to the positive first. So we could have this as 1/5, or if you want it as a decimal, 0.2. Okay? And then if we're going to do 5 to the negative second, and you can just put in 5 to the negative second in your calculator if you want, and you get a decimal. So I'm just going to put the decimal here, 0.04. Or you could do it as 1 over 25. So again, I don't really care if you use the fractions that are decimals. You need to graph it. Either way, you need to have an idea where that fits on your graph. So on my graph here, I'm going to count by 5s on the y-axis, 5, 10, 20, this would be 25 up here, and I'll go by 1s on my x-axis. So I have negative 2 comma 0.4, so that's almost at 0. Then I have negative 1 comma 0.2, not much higher, 0 comma 1, so that's going to be right around there, 1 comma 5, and 2 comma 25. And our graph is going to look as it's going to never get to 0. You shouldn't have this crossing 0, and it grows exponentially. Your curve through those points is going to look generally like this. It's going to be a smooth curve that rises pretty steadily. It's never going to go across this axis. You will never have a y value here that's negative. 5 to any power is going to be positive. It might be a really small number, but even when we plug in negative x, we get a positive y. So understand what that looks like. This is called an asymptote. An asymptote is a line that the graph approaches but never crosses. Let's talk about domain and range. What would the domain be for this problem? Well, the domain would be all real numbers. All real numbers. Okay? All real numbers. You have any x value. Okay? The range would be our y value. So the range, I'll try and fit this up top here. The range would be y is greater than 0. Not equal to, it's not equal to 0, but greater than 0. All the y values are always going to be above 0. Okay? The domain, you could have any x as all real numbers. Okay, let's try another one here. So if we're going to draw this one in, I need to get rid of some of my work from that other problem that stayed with us there. We don't want that anymore. All right, so now when I go to graph this, I'm going to make a table of values. So I'm going to plot some x and y's by making a table of values, and I can do that x and y's, and I'm going to plug in negative 2, negative 1, 0, 1, and 2. All right, so if I plug in 0, right, so I'm going to get 3 times 1/2 to the 0. Again, 1/2 to the 0 is 1 times 3 is 3. That's why this will always be our y-intercept. Okay, we know we're going to go through the point 0, comma 3. When I plug in a 1, it'd be 3 times 1/2, so that'd be 3/2. And when I square it, I have 3 times 1/4, so that's 3/4. When I plug in a negative 1, that's 3 times 2 over 1, because I'd have the reciprocal of 1/2, so 3 times 2, which is 6, and I have 3 times 4, which is 12. All right? So in this case, I'm going to go by 3s, 3, 6, 9, 12 on my y-axis. On my axis, I'm still going to go by 1s, 1, 2, 3. All right? So I have the point negative 2 comma 12. So negative 2 comma 12 would be a point right here. Then I'd have negative 1 comma 6. 0 comma 3, 1 comma 1/2, so that's right there, and then 2 comma 3/4, again approaching there, but it's still never going to cross that axis. So we'd have a graph that looks like this. Okay, still has an asymptote there. So when I talk about domain and range, the domain is all real numbers, and the range is y is greater than 0. I still have all my y values above 0. So, and this is decay, right? This value is between 0 and 1, so we have decay. That's what a decay graph is going to look like. Okay? So you know in general what these graphs look like, so you can see at the end, does it look like my answer makes sense? Let's graph some more exponential functions here. We're going to make a table of values, and we can pay attention to whether we think it's going to be growth or decay. The 0.4 there would indicate this is going to be exponential decay, because that b value is between 0 and 1. So I can plug in my values. I plug in negative 2, I'm going to get 31.25. I'm going to get 12.5. 5, 2, and 0.8. All right, so I'm going to count by 10s on my y-axis, and I'm going to count by 1s on the x. Negative 2, comma 31.25, so a little bit above 30. Negative 1 and 12.5, 0, comma 5, 1, comma 2, and 2, comma 0.8. Again, getting pretty close to the axis there, pretty close to 0, but it's never going to cross it, right? So it's going to level out there as we approach, and that's going to be exponential decay, right? Exponential decay as we move from left to right, getting closer to the x-axis, because that b value there is between 0 and 1. Now let's see another exponential function we can graph. So when we graph this one, again, making our table of values of x's and y's, and you should be trying this, right? Let's see how you can do, and then play the video and see if what you did seems accurate. So negative 1/12, negative 1/6, negative 1/3, negative 2/3, and negative 4/3 for our y values. And so I'm going to count by 1s on both axes. And when I graph this, negative 2, comma negative 1/12, so just a little bit below 0. Negative 1/6, for negative 1, 0, negative 1/3, 1, negative 2/3, and 2, negative 4/3 would be 1 1/3. And we can see here the curve isn't as steep. It's a little more flattened out, but it's still going to curve there. Right? So this value affects, the bigger it is, the steeper the curve. That negative 1/3, it's a little flatter of a curve. It's still exponential growth. It's getting further away from the x-axis as we move from left to right. And so that's what our graph would look like for that. And we can find a domain and range as well. So the domain is still going to be all real numbers. We can plug anything we want in for the x, and the range is going to be y as less than 0, because the y values are all something negative numbers less than 0. All right, looking at this before we see another exponential, what is alliteration? Well, brief break is an example. It's got the same consonant sound at the beginning of both words. Brief break is an example of alliteration. I like English as well. For extra credit, if you email me before the start of the next school day, an example of alliteration in the real world. Give me some example of alliteration in the real world, and you'll get some extra credit points for doing that. All right, let's talk about real-world growth and decay. Real-world growth and decay is written in this form. It looks a little different. We got A, instead of a B, we have 1 plus or minus R. That's because if the rate is growth, we're going to add the rate. If it's decay, we're going to subtract the rate. And we have T because it's time instead of an X. So this is really our Y equals AB to the X. We have A, B to the X. Okay. Our B value, the R here, is a percent over 100. And if it's growth, we're going to add the rate. If it's decay, we're going to subtract the rate from 1. Okay? And T is our time period. So let's use this in a real-world situation. So we have a collector car being sold. So that's going to fetch a good price maybe, and maybe go up in value over time. As we see here, it's saying that it's going to increase in value at 6.9% per year. So recall that A value, right, was the Y value when X is 0. In this case, when time is 0, it's always going to be our starting amount. So this is our A value, right? A is 11,000. Our rate is going to be 6.9 over 100, okay? And since it's increasing in value, right, that's growth. So we're going to add that. So if we want to write an equation for this, we're going to have Y equals 11,000 times 1 plus 0.069, 6.9% divided by 100, and then to the T power. In this case, if the auction took place in 2004 and it was bought in 1984, our T is going to be 20. So we're going to have 11,000 times 1.069 to the 20th power. Right? So we can find out what the value of that car would be 20 years later. So we can put this into our calculator, and after 20 years, we're going to find that it's $41,777.92. We'd round money to the hundredths there for our pennies. Okay, so keep in mind, our starting amount, that's your A value. The rate, you're either adding or subtracting the percent divided by 100 from 1, and then our time is our exponent. All right, let's see another one. All right, so in this example, we're seeing ponderosa pine, which are decreasing. So decreasing, that means we're going to subtract our rate from 1963 to 2002 by 0.5%. So 0.5 over 100 is going to be our R, and we're going to subtract that. Our starting amount is 41 million acres, so our equation is going to be Y equals 41 million, and then 1 minus 0.005, right? 0.5 divided by 100, and 39 years. From 1963 to 2002 is 39 years. So we put that in our calculator, we get about 33,719,724. We round up to a whole tree, okay? So that would be about how many trees we'd expect there if it's decreasing by that 0.5% every year. So we can see there exponential equations in the real world. A is that starting amount, right? A times B to the X. B is the growth or decay. We have to look in this case if it's up or down by some percent. We factor that in to find that B value, the growth rate or decay factor. And when we want to graph these, we can make a table of values, plug X values in, get Y values out, draw that graph. Keep in mind writing the equation, right? The A value is always the Y-intercept, the Y value in X is 0, and we can find the B value by taking Y's and subtracting the number before it. You'll get whatever that factor is that we're multiplying by to get the next Y values in our table and write that into our equation for our A and our B values to the X.